Okay, so in this video, I'm going to describe for you several different ways of representing a circle. The first way of representing a circle is very simple. You've all learned it in your algebra class, and it is simply to say x squared plus y squared is equal to 1. This is a representation of the circle in the Cartesian coordinates. The next way of representing a circle is also very simple, and you have learned it before most likely, and it is to say that the coordinate x, y is equal to cosine of theta, sine of theta, where theta is an angle between 0 and 2 pi, and theta represents on the circle this angle between the x-axis and a point on the circle, a vector to this point. So this is two different ways of representing the circle. Now let us talk about a third way of representing a circle. The third way of representing a circle is to write the equation E of h is equal to h squared minus 1 over h squared plus 1, comma, 2h over h squared plus 1. Here, h can be any number or infinity. Why infinity? Because we need that in order to complete the circle. Let us see what happens. If you take h equal to 0, you will get minus 1, 0. So this point here is h equal to 0. If you take h equal to 1, you will get 1, 1, 0, 1. So you will get h equal to 1 up here. If you take h equal to minus 1, you get 0, minus 1. And in order to get this point here, you need to take h equal to infinity. If you know calculus, you can see from the limits here, this is 1 and this is 0 if you put in h equal to infinity and take the limits. This here is a third way of representing a circle. Now let us look at another interesting case. In this case, we will represent the circle as a three-dimensional string, which is a loop. So this here is a three-dimensional loop, which is a circle. Now, if we look at this loop topologically, it can also be knotted down. For example, with this knot here. You can start anywhere on this knot, and if you traverse your way through this knot like this, you will realize that you have come back and completed the loop. This knot here is called the trefoil knot. And this knot here is called the mirror trefoil knot. All of these are said to be homeomorphic in topology. By homeomorphic, we mean that these are essentially the same object in some sense, in terms of their shape. Next, we will come to another representation of the circle, which is a representation of a circle for a two-dimensional object. I don't know how many of you have read this book called Flatland, but it's actually a very interesting book, and the whole book is from the perspective of how it would feel to be a two-dimensional creature. So let us take this two-dimensional creature and show him what it means to loop around. A two-dimensional creature is typically used to walking in a single direction and if from point A to point B. Now, if you wanted to show this creature what is a loop, you need to get him from point A to B, and then without him turning around and going back, he should be able to go from back to point A. So in 3 dimensions, we can fold this line on him and do something like this. So thereby we merge points A and B in 3 dimensions. And this one-dimensional creature, as he walks, he's thinking he's walking in a straight line, but eventually he comes back and has looped around. This can be done using just a single point and making a circle out of that. It can also be done by giving him 2 different line segments, AB and again B to A, and we can just jump him from here to here, and we can just jump him from here to here. So in 3 dimensions, we would be making a fold something like this of the line segments, thereby showing him what is a circle. Next, let us talk about how we can get a circle by doing translations on lines. We can get circles by doing translations on lines in the following manner. You take a line and then you represent it by this being a translation to the right and T inverse being a translation to the left. Now consider this. You take this translation to the right and this translation to the left, and you create what we call an orbit. An orbit is essentially taking some point here, going 1 unit this way, going 1 more unit this way, 1 more unit this way, 1 more unit this way. And same thing in T inverse. So going 1 unit behind, 1 unit behind, 1 unit behind. This set here of this point, this point, this point, this point, this point, this point, and this point is called an orbit. Now, if you take the case of these orbits and you take the set of all orbits, so you take orbits from here to here, then you will have looped this set of orbits around. Therefore, this set of all the orbits on this translation T and T inverse is topologically equivalent to a circle. This is a very important concept that can help you visualize and understand what it means for things to be topologically equivalent or topologically homeomorphic. Another representation of a circle in topology is to take the plane here and then take the subspace of all one-dimensional objects, which is all of the lines passing through the origin. If you take all of these lines, there's a way to get the circle here as well by defining the circle not to be the unit circle, but to be this circle here. This circle here, for each line which is on the one-dimensional subspace of this plane, there's exactly one line that corresponds to a unique point on this circle, except for all of the lines intersect here, so but we remove all of the other lines from this point except the line x equals to 0. And that is yet another way of representing a circle. Thank you. I have shown you several different ways of representing circles, and I hope you have enjoyed this video.